Okay, welcome to the class. Um, we are now, I think, in the hardest part of the mathematical issues of the course. We have this one, this problematic one. Not really problematic. I mean, like it's difficult because it's a new way to look at things with, through probabilities, and it's not a very common way to look at life. So I think this is the most hardest part regarding the Poisson neuron. Therefore, in the following Sunday reinforcement, I'm going to show again the proof of the relation between binomial distribution and Poisson distribution of the Poisson simulation, which is one of the first things that you need to do in your second project. Okay, you need to simulate the neuron, and I want you to understand the idea behind it and not just the steps that I will show you today. So this is regarding the Poisson simulation, and also the next subject, which is called in Izhar notes, single and multiple point processes, about autocorrelation and cross-correlation and hazard functions and so on. It's also the hardest. And I think that then we arrive to some of the, it is not becoming easier, it's just that you are becoming used to this kind of talking. So if you feel that you didn't understand anything, it's okay. You are not alone. It's always like this in the course. Specifically at this stage, and we are here to do it together. Okay, great. So today I want to cover two subjects. The first one is of tuning curves, that I understood that some of you are not fully acquainted with what the tuning curve is. Is that am I right? Okay. So can I ask from someone who thinks that he knows what tuning curves are, please to explain to the class the idea behind tuning curves, a very, very important subject in neuroscience. Yes. Yes, Austin.
It's a plotter function that shows the relationship between one dependent variable in a stochastic process and the predicted output for a process that's not necessarily binary.
Let's go into something which is easier. Okay, let's not relate it to the stochastic process and so on. What is the x-axis over here? Also, always in tuning curves. Yeah, inputs, stimuli. Okay, when we talk about neurons, it's commonly the stimuli. And the y-axis is the firing rate or a specific response of the cell. Okay, and then the idea behind tuning curve is something that Hibel and Wiesel discovered and got a Nobel Prize for it. Is that when you take a neuron and then you present this neuron with stimuli, okay, for example, horizontal or vertical bars, for example, then you can see that the neural response of this neuron changes in relation to the stimulus that is presented, right? So you can see, for example, I'm sorry, Austin, by the way, it was a very, very good explanation. I just want to start from somewhere else, okay? So, for example, you can see here that we have a horizontal bar, and for this neuron, its firing rate is very low. And the more we come closer to a vertical bar, the responses in the spike length are becoming higher, right? Now, during your first project, and also we talked about it in the past recitation, we learned about how to take these kind of spike lengths and convert them into firing rate function, right? That you have the firing rate firing rate over time. Do you remember that? Now, I wish to ask you, when you have these different kind of responses, how would you describe them mathematically? Because we're in science, we want to describe the phenomena, we want to describe them mathematically. How would you do that? How would you relate between the different responses here and the tuning curve here? Yes. Find rate according to angle.
Mm-hmm.
Taking the drops.
Great. Okay.
Did you understand? I want to show you. So if I take, let's say that a horizontal line, we will call it stimulus number 1. Okay? And a vertical would be number 2. And then I'm going to create this firing rate function, right? Like in the second question in your project. And I will see that for 1, I have about a straight line. Okay, and let's say this is the stimulus onset. And then for 2, I'll use another color. For 2, I have this increase in firing rate due to the stimulus onset. Okay? Now, what offered, Notella, you are? Ofek, great. What Ofek said that we want to see the differences between these two curves, right? So what I'm going to do is take a specific time, specific duration, for example, this duration. And then what I can do is to say, okay, I'm looking at this duration, and I take the average of response here, and the average of response here, and then the average here will be this, let's say 10, and the average of response here will be here, for example, 50, okay? And then I can plot such a tuning curve where the beginning for the horizontal line begins with 10 spikes per second. And here for the peak, it is 50 spikes per second. Now, what I want to ask you is, what is the problem with such a model? Because we did describe things mathematically, but now we have a problem. It's an open discussion, and therefore any comment is welcome. Great. Okay, so first of all, you need to decide what is the relevant interval. You're right. Yes.
Is to if they are different neurons or maybe even the same, but have different starting activity.
Exactly. So you say that, for example, in one trial, the neuron responded like this, but in the second one, it responded like this, right?
Yes.
So what value should I write here on the tuning curve? Right? So what would you offer to do? Such a great, great. So we have 3 approaches regarding the value that we write in the tuning curve. The first one says, okay, take this whatsoever bin and just write what is the firing rate. And the second one says, look at the bin here and look at another duration here, which is called the baseline. And then you can do 2 things. The first one, the dynamic approach, says take this and subtract this from this measure, right? But just by subtracting, and therefore all the tuning curves will begin from 0. Not the tuning, sorry, all the curves, the firing rate curves, right? So this is one approach. Another approach says normalize it to baseline. Therefore, divide the value here by the value here. And this is different. This is called the normalization.
Which one is better? Should we subtract or divide? What should we do? Why should we use one of them?
I'll write it on board. I'll ask again in Hebrew. So, אז יש לנו שתי גישות. גישה אחת אומרת נחסר את הבייסליין, והגישה השנייה אומרת נחלק בבייסליין. איזו אחת היא עדיפה? לחלק בבייסליין? כן. לחלק זה לעשות נרמול. לא עשיתי בעבור כאן.
So which one is the right one to use? What is the difference between subtraction and division?
I think might be more.
Okay, so if I assume that the dynamics of the neuron regarding the firing rates are just the same, and the only difference is where they start, right? So I can take this neuron, subtract, and then this neuron will look like this, right? And then I can take all of the beans over here and write them here on the tuning curve, and of course the standard deviation and so on, right? And please know that whenever you bring us a plot that you plotted, I ask you to add the standard deviation or the normalized standard deviation so that we can see also the density and the distribution and not only the expectation. Just a small remark that I'll keep on repeating. So the problem here is that sometimes the beginning of the increasing is different, right? And this might be due to the fact that we didn't divide with the baseline. Therefore, some people say that you better divide by the baseline, and then you have about the same latencies to increase of activation. And this is just another vision. Anyway, whatever method that you're using, you need to justify your reasoning, right? So already in your first project, you are asked about the tuning curves, and you are asked also about the duration of the beams and where to start and where to end. And then you need to decide whether to normalize or subtract or what is your baseline. And you need to justify your claims, okay? Because this is scientific work. Yes. Yes. I'll re-explain it in Hebrew. So, בכל פעם שאתה מפחית, I'll say it in Hebrew and then in English again. בכל פעם שאתה מפחית, אז מה שקורה לך זה שאתה רק מיישר אותם שהם התחילו שניהם מאפס. אבל עדיין אחד יכול להתחיל לעלות קודם, נכון? אז אם אתה רוצה לצמצם את ההבדלים האלה, אתה מחלק, ואז הנרמול גורם לזה שהם יתנהגו פחות או יותר גם לאורך הדרך אותו הדבר. אוקיי? So, what they say that the dynamics between different trials might be different. For example, where does the neuron start increasing its firing rate, before or after? So if you only subtract, you will say the same dynamics of earlier increasing or later increasing. But if you think that the main idea is how you normalize all of them by division, and therefore most of these curves will look just about the same, increasing about the same place, then you use the division.
About the sheet of where the stimulus affected the, I don't
Yeah, the beginning of the increase.
But it doesn't really change like the data, like what we want to see.
Yes,
But
it is very commonly used.
then
Yeah, it's a good question. Therefore, every time that you read a paper and they write you a tuning curve and they write you this is the time that you took the normalized firing rate, you should ask yourself, did they choose the right way for calculating? Maybe they distorted the data. You're right. This is a very, very good understanding of the subject. Thank you. Okay, so this is about the tuning curves. Now, I want to show you some other more philosophical problems regarding the tuning curve. So the first one is one of my favorite papers, quite a revolutionary one. So first of all, who said that there is a preferred stimulus for a neuron, right? So the fact that we find a correlation between specific neuron and the stimulus does not say that, okay, I'll give you one example. I just saw an amazing paper that I thought about giving you reading it, but then I said that it might be a bit too confusing. That in this paper, they show that if you first saw a horizontal line and then you saw a color, then you will have a tuning curve for colors. But if you didn't see the horizontal line before, you won't have a tuning curve for colors. And this is, I think this is an amazing one. It's really mind-opening, the fact that tuning curves are highly dependent on what was the stimulus that was shown before and what was the reaction to the one that was before. Therefore, there might be a possibility that what we call a preferred stimuli is something that might change all the time, not only by plasticity. It just might change because neurons are not that discrete. Another thing that we really like about tuning curves is that we believe that these are injective functions. Therefore, injective, and we say it in vivo, פונקציות חד-חד ערכיות. Therefore, that if you know the tuning curve of a neuron, then you can guess what was the stimulus, right? And you have a question about that in your fourth question that you are asked. What do you think is the stimulus that was presented when you have these tuning curves? And this is a really nice question because it's not always that you can go back to what was the stimulus. You can't always decode the neuronal activity. And the last one is, again, one of my favorite papers, that in these papers, whoever is doing Hamutal course will also present the paper or see. So the idea behind it was a very nice question that was raised by a student from the first degree in this lab, that he said, how do we know that we show all the possible stimuli to a neuron? I'll say it again in Hebrew. איך אנחנו יודעים שכשאנחנו עושים ניסוי לעקומת תמנון, באמת הצגנו את כל הגירויים האפשריים. Therefore, they created a deep network design, that in this design, what they did, okay, so they recorded from a monkey IT area. This is the place which is commonly related to faces. And then they took these neuronal responses as a kind of a feedback to the deep network. And the deep network needed to optimize the firing rate of the neurons. And then they asked themselves, what was the stimuli that this deep network generated? And it's really funny because these stimuli are really strange. I don't know how good you see it, but this looks like a kind of a distorted face of a monkey or something like that. So therefore, instead of just showing all possible natural images, they took the deep network and let it guess the preferred stimuli. And by so, they showed that when we create a tuning curve, we have this assumption that we know the possible stimuli that can be presented to a neuron, but sometimes they are not even real stimuli. Sometimes it just reacts to something strange, but we don't know what it is. Okay, so this is really, I love this paper. I can send it to you. And there is also, oh, maybe you see it here. It's fine. So it began with the monkey here, as far as you can see. And then it became something like this, like with two black eyes and a strange mouth, and it looks like nothing. So You're welcome to open it. It's very nice. Okay, so enough about the tuning curve, and now, before we will have a short break, I wanted to talk about stochastic processing. So, Austin, you've been really generous. Can you please explain us a bit about what stochastic processing?
It's really a process that can be repeated multiple times and
Okay.
replicated in different settings.
I think that this is like a kind of an ergodic process, right?
Well, if they perform the same in every situation and setting, but they can
Yeah.
change their performance depending on the age, the time you do it, or where you do it, what you do it with. It's
Okay, so you say that there are a lot of possible implications or variables that can impact a result of a process, right?
Yeah.
Okay, so I'll just say something a bit different because I want to be a bit more accurate when I say stochastic process. And the reason is that you're right, but you're more relating to a ergodic process. And I want to distinguish between ergodic and stochastic. Okay. So what is the idea behind stochastic process? So not very long ago, about 100 years, there was someone who was called Markov, that you probably have heard of. And he said that whenever we look at possible events, we can model them by something that is called a stochastic matrix, okay? Now, this is a very, very simple idea to understand. So I want you just to listen and understand now, because sometimes people say Markov and stochastic, and it sounds like they say something really terrifying, but practically it's very simple and quite elegant. Okay, so let's say, for example, that we have a frog, and this frog sits on this leaf, right, on the water, on the first leaf. And then this frog needs to jump to another leaf, for example, the second one, or the third one, or the fourth. We can ask ourselves, what probability we have that the frog will jump between these specific leaves, okay? I'll re-explain it in Hebrew. אם יש לנו צפרדע שנמצאת על הלב, והיא צריכה לקפוץ בין העלים השונים, אנחנו יכולים לשבת ולשאול מה הסתברות הקפיצה שלו בין העלים. So if she started here, she has a probability of third to jump into two, or probability of third to jump into three, and so on. And now we can take all of these connections and model them as a matrix, which is called the stochastic matrix, and also the transitioning matrix, right? Because it's the transition between the different flips. So, for example, the probability that the frog will jump from the first flip back to the first flip is 0. She won't jump to the same flip. But the probability that she will jump from the first to the second is 3rd, and from the first to the second to the third is 3rd, and from not 3rd, I mean, like, how do you call this number? Sorry, 1/3. Yes, and the probability that she will jump from the first to the fourth is also 1/3, right? So we can model all of these possible events by a matrix. And now we can ask questions about this matrix. For example, could it be diagonalized? And it's really nice because the diagonalization of this matrix, if we're talking mathematically just by definitions, this is the stationarity of this matrix. But it's irrelevant for this because we talk about stationarity about something different. But the main idea is that we now, instead of looking at just probabilities, like in a density function and so on, we look at it as matrices. And with matrices, we have new tools that we can use, and they mean something different. So in a way, when we say stochastic, it's kind of saying random, but organized, right? Because at each moment, when I come to this system, every time that I come, I have a different probability regarding where will the frog be, right? But I'm still organized because I know how she jumps between leaves. Now, a very nice question that I heard last week when I talked with one of the students about it, Noah Nagar, she asked me, okay, but let's say, for example, that this frog jumped from the first leaf to the third. Is she affected by the fact that she was already in the first leaf? For example, who said that the probability of going back is still third? Maybe she is affected by the fact that she was already there. So when we talk about Markov models and we talk about stochastic processes, it's called memoryless processes. What does that mean? This is called the Markov property. It means that we don't care what was the last leaf that I was in. It does not affect the stochastic matrix from now on. Each time it's kind of rolling a new die, and I don't know what will be next. Now, when we talk about neurons, and we want to talk about this kind of memoryless property, is that we believe that neurons are unaffected by the fact that they were already spiking, okay? So look again at this figure. And let's say that we want to model a neuron, okay? So, you know what? I don't want to talk yet about modeling neurons in a minute. I want just to define another important thing, which is called the different types of stochastic processes. Any questions so far? Okay. So the last thing that I want to define is the stationary and ergodic processes, okay? So what does that mean? Some of the stochastic matrices are also stationary. This is like kind of a down label of stochastic processes. It might be also stationary. What does stationary process mean? It means that the same distribution is the same all along the process. Okay, for example, if I have a neuron and I just record this neuron, it should not be affected by anything. It just needs to give me again and again the same results. Okay, the same firing rates. Yes.
I'm sure I understand. If there is fatigue, for example, stationary cannot assume the result.
Yes, right. So, I'll give just another example. Maybe it will be a bit clear. So let's say, for example, that I have this kind of neuron and I have this spike zone. So this is during the first second, and here I have the second, and during the third second, I have this, okay? So you can see that the organization of spikes within each second is different, right? But the number of spikes is the same. Therefore, this is like the kind of this random, this is kind of this organized randomness that we were talking about, because you don't know for each second how the spikes will be organized. But you do know that there will be, on average, 3 spikes per each second. Okay? So this is not a regular neuron. A regular neuron would look like this, that you have the same eyes, the same interspike intervals between every neuron. But in stationary, it's not the same, but it acts about the same. So how do we measure this stationarity? We look at the distribution all along the process, and then we can count these distributions for example, the distribution for a spike within each beam. We can look at all the possible moments of third moment and fourth moment. This is called a strong stationary process, and we never try to check this. What we do try to do is we check for a weak stationary process, and then we check for the expectation. So what is the expectation within each beam here? Right? And sorry, it should have been the variance, please. And the variance within each one. So here it looks also almost a uniform, so the variance is wide. And here the variance is skewed, okay? So for example, here, although the expectation is about the same, the variance is different, okay? But whenever we have about the same expectation and variance over time, they are constant. Therefore, this is called a stationary process. And please know that this is over the dimensionality of time. So if you want to check if the process is stationary, you need to bin it into possible bins of time. For example, at the beginning of the trial and by the end of the trial, and then you need to calculate the expectation and the variance, and then you can decide if this is a stationary or not. But again, look at the time axis, only at the time axis. Yes.
So in this case, the first neuron will be stationary, right? Because the variance is different than the
No, in this one, it's not stationary, right? Because the variance is different. Yes. Can. So I'll say it again in Hebrew. אז תהליך סטציונרי במובן החלש, אתה תיקח אותו לאורך הזמן, בפרקי זמן שונים, בכל פרק זמן אתה תסתכל על ההתפלגות של הממוצע והשונות.
לשאול את זה שתלוי בדלתא T שם, תלוי בזמן שלוקח, אז התהליך הוא נשאר תהליך כאילו רק לזמן שאני בודק, לא? אני מגדיר אותו רק לנקודת זמן שאני בודק, אני לא יכול להגדיר תהליך כתהליך כאילו...
אז בתהליך סטציונרי זה יהיה נכון לכל פרק זמן שתבדוק. So, please again your name, Amit, sorry. So Amit asked a very good question. He said, but this is highly dependent on the size of the beam that I choose. So therefore, a stationary process, a strong stationary process, will have it for every time beam that you take. And the weak one will have it, for example, for big time beams. Okay, but it should be right for all the possible time beams that you can take. But just, kind of use it logically. Yes. So for example, if I take here 1 millisecond, so it won't be right. But if I take 1 second, it should be about the same. Yes.
Sorry, why it's not stationary? Because it's 3 in each, so the variance will be.
I'm not counting the spikes, but let's say I'm counting the interval between. Yes. Good question. Yes.
So an ergodic process with the stationary process.
Yes, an ergodic process must be stationary. Okay. So although ergodic looks again about the same idea of expectation and variance over time and over trials, right? Therefore, for example, I had like a class question. Do you have some examples for these types of stationary yet non-ergodic and so on? Okay, I want to show you some examples, so maybe it will be more clear. So whenever I roll a die, rolling a die is a stationary and ergodic process, right? Because it should not be affected, the variance and the expectation should be the same within each time I roll the dice. Right? Great. Now, birds on a tree every day, we know that the birds are not always on the tree. They come and go, right? So therefore, this is stochastic because I have a probability of number of birds on the tree within each hour. But it is not stationary because along the day, the number of birds changes. Another example, which is nice, is the average time of sport for every man. So if I take a week, let's say there are some people who does 3 times a week, they do running, and 2 times, or some of them don't do. So for each person, it's kind of a stationary process, right? For how long you're doing your sport, your sport habits, it's kind of a stationary process. Yet it is not ergodic because between persons, between subjects, it's different. Okay? Yes.
About this translation, one of the other problems is that the translation.
Yeah, so strong stationary process commonly don't check it, but first of all, for a weak stationary, if you have at least one bin that's for this one, the expectation and the variance are the same. So you say that this is weak. For stationary process, you will check all the possible bins, and you will and you might check also higher moments such as fewness and what was the other one? Kurtosis, yes. Yes.
About the stationary, I was thinking, for example, the weather. Let's imagine that there is low minus wind. And the temperature per year, like each year, should have the same distribution. So we could say it's stationary, but between each month, it's not. So how do we know which window we choose?
Okay, so some of the definitions are a bit confusing. So it's always a question of what is the bin size. The idea of temperature is very good because if you take day or if you take month, it might be not the same, but across the year, it's about the same. Yeah. So this is kind of a stationary process because across the year, there is at least one bin that it's about the same distribution. But the problem is that you don't have like different kind of years, right? But let's say within a decade, if you check every year, this is problematic. It's not like people that you can talk about inter-subject differences and so on. So you might say, some people will say that it is ergodic because across different years, it will be the same distribution and so on, but some people will say that it's not. So if we stick into the most clear definitions, it should be across different subjects, different trials. Yes. Yeah. Again, some of the definitions are a bit confusing, but therefore, for this reason, in the project, we did it across subjects, and you have for each subject a duration, and then it is more clear how to use. Yes.
Could you think of ergodicity as some like continuous metric rather than black or white? So like if the space ergodic as you decrease the bin size, then it's more ergodic than another process that it needs a bigger size.
Yeah. It's also a possible way to look at it. Yeah, it would be fine. Do you need a small break? 5 minutes break?
Yeah.
Okay, let's take a 5 minutes break. And at 2:47, I continue to Poisson neuron. כן, כן, כן.
הם טעו?
לא, לא, לעיתים זאת הנוסחה שלי.
אוקיי, אז
יש גם הרבה
איך אני
נוסחאות.
יודעת מתי אני עושה בסביח ומתי אני עושה ממוצע?
את מגדירה? בפועל את
לפי מה שאת אומרת, אבל אני מתחילה בלחפש את הממוצע, אני לא יכולה להכריע תקן.
ספציפית בשאלה שאני נתתי, זה היה להשוות בין הממצאים.
ואיך הייתי יכולה לדעת את זה, כאילו, לפי הנתונים בשאלה עצמה? אוקיי.
אבל אפשר גם היה לשאול, אני מבינה את הבלבול של...
זהו, כי יש כל כך הרבה נוסחאות, דווקא זאת הופיעה הרבה יותר פעם, כאילו אצלנו.
כן, נכון, כי בדרך כלל לוקחים באמת את הווריאנס, אבל נגיד אצלנו בשאלה בקורס, אז אני למשל הקפדתי שזה יהיה האמפליטודה של הרעש. ואז זה בכלל אחר, נכון?
כן, אני יודעת, זה מה שבלבל אותי, גם אמרתי, לא יכול להיות שאני לא מסתכלת על הממוצע, כאילו, אני צריכה לחשב אותו ישיר.
נכון.
אני חושבת שבכלל אני צריכה לחשב אותו ביחד עם סיגנל.
זה הכל עניין של הגדרה. יש את זה, יש את זה, זה באמת עניין של הגדרה. רפי נתן לכם את מה שנפוץ אצלו.
הבנתי. אז בקורס הזה אני לא מסתכלת על, כאילו, אני יודעת שאני...
שוב, אין פה משהו אחד. בקורס הזה את צריכה להגדיר, הסתכלתי על א' וב',
אוקיי.
ואז להשתמש.
זאת אומרת, אם הייתי אומרת לך, הגדרתי לפי זה, אז הייתם מקבלים את זה?
כן, למה? זה יצא לך לפי ההגדרה של זה?
לפי החישוב שראיתי, אז כאילו, כן, זה יצא, אבל זו תשובה אחרת, זה כאילו...
ואז קיבלת את זה.
לא, אני בסוף כאילו הסתדרתי, אבל חברה שנגיד, היא אמרה, היא קיבלה שישית פשוט, אתה לא הבינה למה.
בסדר,
לא, זה סבבה.
אז זה בסדר.
סגור, תודה.
Yes. I'm not very good at drawing on this, but I can draw it again here. So let's say that you have this plot of iron gray, right? And you had this first file that looks like this. And then a second file. If you
same neuron, right?
for the self stimulus, same neuron. And then when you only subtract, what you will have is you will have this, right? Is this okay? I just shifted it. But there are still differences, right? Very big differences.
Okay. Oh, so you just, when you say you subtract, you mean you subtract
The baseline.
the
Okay.
height
Yes.
exceeding from one to the other?
Yes. So I just take all of them to begin from the same side, the same place.
So you cut the y-axis that corresponds to the extra.
Yes.
Okay.
Exactly.
Okay.
So another possibility is to say, I know that when a neuron is more excited, there is a higher firing rate anyway. So for here, at the baseline, it was already more excited. Therefore, the right thing to do is not subtract, but to normalize. And then when you divide this by this, you have this kind of this more close kind of curve.
Okay, but in this case, it would be dividing it by the x-axis, not on the baseline, right?
The y-axis. Each time I take here and here, and I divide. I can either subtract or divide.
And you divide all the time.
Yeah, here, for example, I took this movement window, and I just divided each window within the baseline. Yes. You're welcome.
Do you think we can check the ergodicity break formula from the project?
You can, excuse me, you can check the ergodicity break
Yes.
formula. What do you mean?
For the project, we have
Yes.
to calculate this, and the terms that they use is subsample and total sample. So I'm not sure if total sample means all the 200 subjects that we have in each data file, and subsample would be just one
Yes.
subject.
One or five or whatsoever, any possible number of subsamples, right? Because this is the idea behind ergodicity, that you take it for every possible subsample. I think that this is what they were talking about.
Yeah, but I felt that we were using just one
No.
sample against all of them.
No, if you take every subsample.
So I decide the number of subjects that I use.
You can either decide, but I think that in the paper, they say that you need to check every possible subsample size, right?
But if I
If
check,
I'm not wrong, I'm not fully
That's what I don't understand, because if I check each one of them, it would be, can I write in the board?
Yeah, but I need to go back to the class, I'm sorry.
Sorry.
Sorry, yeah, oops, a bit, because at 3:45 I have to go to the field.
Okay.
Great, you're welcome. Sorry, Chris, is it short? Okay, but we have also the reinforcement on Sunday. You can keep the questions so. But I would check all possible substances if it answers you. Yes. Exactly. Hello to ergodicity. Yeah, it's nice to understand, right? Okay. So now I want to talk about the Poisson point process, and for me, we finished everything that you need to know regarding the first project. And now I start talking about your second project, which will be uploaded by this Sunday, and it will be the date of submission will be the June the 3rd. Okay. Don't worry, there is a lot of time for until July for your next project.
So it has changed, right?
Yeah, it will be the June the 3rd.
But that's for the, what?
For the second project.
Because before.
Now, I have an important, it's not really an important question, but I want, Sophie, I need your help. For example, in a poll or something like that, some student told me that there is a feeling that the projects are very, very heavy loaded, and that there is not enough time to work on them. So my question is, would you rather to split it into smaller projects of 1 or 2 questions within each week? But it's about the same projects, or would you prefer to leave it like this, that you have once in every 2 or 3 weeks, a big project? So I think that the second option is better, but last year some students did ask to shift it to the first one, that you have every week about the same load, and it's about the same. It still takes about 2 days each one. So now it's instead of 4 or 5 days. So I thought that if you have more time, it's better that you. But this is my point of view. So please let me know if people prefer that it will be shorter projects of, for example, 2 questions, but they need to submit it every week.
I can do the poll in this call, but I know that project is registered or not, so that is not fair.
No, do it on her. And you can talk with Noah, or you can do it on Discord, and she will do it with the Hebrew speakers, okay?
I was also thinking that obviously talking with the students and you, if it was possible, instead of just having one session per week of 8 p.m. to 10 p.m., maybe 1 hour one day and one another day, because sometimes questions do not come on Wednesday. So if we could maybe split these 2 hours.
So it's split between the subgroups of the students, but what I can do is that I can, in some weeks, I can add another hour. Okay, so for example, this Sunday, I'm going to do another reinforcement for Hebrew speakers also on Sunday. And if you feel that you need also, and I think that maybe the week after, I will do a big reinforcement, mathematical reinforcement, only about all these point processes and so on, because this is also a very hard mathematical issue. Okay, but speak with Sophie, or we can figure out an idea. You're welcome.
And about submission, there was a question about how to submit. Do you prefer like a full notebook,
Yeah.
or is it possible to answer some questions?
Whatever is easier for you, but no screenshots of codes. this really makes me angry to see such submissions, okay? And don't attach your code as a supplementary and so on. Either Colab, Jupyter, or a Python code. Okay, this is like the minimal request. Don't just kind of put it in the end of the PDF. And of course, PDF is the best way to submit. And by the way, we mainly check the things that you write, I must say, because we all live in 2024 and we know that all of us are using ChatGPT. So therefore, you are not asked to submit too many codes, right? We check only one code and we wish you to solve it yourself, not by using ChatGPT, as would be requested in his R quizzes. In the program in his R quizzes, you won't have the possibility to use a ChatGPT. So maybe a project will be like this small question will be a good preparation for you. But when we see something that is not that is strange about your writing or your figures, then we go into more details with the code. But we won't check all the code, so don't wait for any comments regarding the code. Okay, but you need to submit it anyhow. Okay, so now I want to talk about Poisson point process, and now I want to take this idea of the jumping frog into our field of neuroscience, and then I want to do something a bit different. So let's say there was this leaf that says neuron fire at a very exact moment. And now what I want to do is that I want to make a very simple model to neuron firing. Now this model, finally, you have two directions that you can jump from firing into non-firing and from non-firing, not unfiring. And from non-firing into firing and so on. And this is a very ancient model called the Boltzmann model of neuron. And this is a very simplistic one. And it did not work. It did not simulate neurons or spike brains. And for this reason, we study at this course. One of the things that we want you to know how to do is how to model. And when we say model, this is a very common thing in neuroscience nowadays, that you have a phenomena and then you want to offer a model, an equation that explains the phenomena. For example, is it a Gaussian? Is the firing rate is an elevation, and so on. So not only to describe, but also to predict. Okay? So what we do in this course, we teach the first and most common prediction of neuron spiking frames. And this is the Poisson neuron. So the difference in this model is that instead of looking at the transition between firing and non-firing, we look at the transition of neuron fired and then waited 1 second to fire again. So instead of just events, our events are how much does this neuron will wait until the next step. Or waited 500 minutes, or waited 0.02 minutes, right? So now we have how many possible number of jumps do we have? Infinite, right? Do you understand why? Before we were talking only about 2 possible events, and now we have infinite numbers of times that this neuron would wait. And therefore, this is the reason why we say that Poisson neuron is a continuous process, okay? Because we have infinite number of future events that can happen. So a nice way to draw again this neuron is to say, let's say that we have this lead that is fired. And now we have all the numbers on the number axis, that each one of them could be a possible lead, right? And these are very, very, very small leaves, and each one of them is sitting exactly at only one point of time that you wait. Is that clear so far? Now the expiring again, we have a probability for each one of these jumpings, right? So for example, if a neuron fired, then the probability that we will wait only 0 seconds until the next fire is 0, right? So this one is P equals 0. Now now another possibility is that the neuron will wait infinite time until the next firing, right? And this is also here at infinity. This is also 0. So the only question is what happens in between? How does these probabilities look like? And the interesting thing is that these probabilities are taken from a Poisson distribution, which really looks like a normalized distribution, but it's a Poisson. So for some neurons, the most probable duration will be over here, for example, 500 milliseconds. Okay? And for other neurons, it will be much before. Okay? So the most probable, the most expected value is the one that determines the stochasticity of the neuron, right? This is just about the difference between neurons, because some neurons are commonly just firing all the time, and some of them are waiting, right? So the only question is, what is your most probable value?
How do you know that that's like Poisson, not like a normal distribution? It's the meeting like not.
Yeah. So the reason that we say that it's taken, okay, this is a good question. Because practically,
I mean, I think it's I was trying
yeah.
to explain, but I didn't get it.
So what I want to say is that a Poisson has a relation between the Poisson distribution and exponential distribution, okay? You know what, this is just about the next one that I want to talk about. Okay, because when we look at the Poisson neuron, I want to be just a bit more exact, okay? I was just explaining this idea with the list because I think it is more clear like this. But now I want to be more accurate. Okay, so I want to change a few. So a Poisson neuron is not exactly about how long did the neuron wait until the next spike. If I want to be more accurate, the Poisson distribution is how many spikes were there within a possible bin. Okay, so let's see here, for example, this is one of the questions in your recitation quiz, so I would really listen and understand it fully. So let's say that we have a neuron, we have a sample rate of 1000 hertz, which means that we have a bin within each 1 millisecond. And this neuron has a firing rate of R equals 20 spikes per second. So the Poisson distribution is around 20, okay? The 20 spikes per second, this is just about the most probable value, the most expected value of number of spikes within each second. What is the probability of 4 spikes within 12 milliseconds? Okay, so we have the following illustration. So for example, we can have one pattern of 4 spikes within each of these 12 milliseconds, okay? And we can have another one that the 4 spikes were like this, and another one that they are like this, right? So we need 4 spikes that are happening within all the possible 12 beams, and another 8 with no firing rate. So this is kind of a binomial distribution. So we can say in a beam of 12 milliseconds, we have 4 number of spikes. So I have 12 over 4 number of organizations of the spikes across my beam. Now the probability of firing is R multiplied by delta T. R is the firing rate, delta T is the size of the beams, and I normalize it by 1000, which is my sample rate, right? And we have 4 like this is, therefore the power is 4. And then I need to, how do you call it? I always forget that you need the other beams that are not firing. Do you know some of the Hebrew speakers? המרחב המשלים? No. Exactly, these failures of spiking. So this is just about the failure. So it is like this. And there, when I have this is the probability of firing. Now, what is R showed you that if you take a delta T that is also almost reaching towards 0, then this distribution becomes the Poisson distribution. And I will re-explain it again on this Sunday, okay? So when I was talking about these sleeves, I was not very accurate, because if I want to talk about the jumps in time, this is not taken from a Poisson distribution, but rather from an exponential distribution, okay? Now there is a relation between the Poisson and the exponential. They are derivatives of one of another, and the lambdas are about the same. But again, I wanted you to fully understand the relationships. Okay, so is that more clear now? Yes.
Can we clarify the difference between the interarrival times and the exponential? And
I didn't
the
understand.
interarrival times in
Yes.
this case would be what's exponential?
Yes. So you have a very high probability that you won't wait for long until the next spike, and then it deteriorates within time.
Yes. But the spikes per se are Poisson or approximate.
Yeah, we approximate the probability of spike within a very small beam.
And that's Poisson.
Yes. And the reason that I'm showing you this is that when you simulate, right, so I said that there is a relation between the binomial distribution and this is a good approximation for simulating a Poisson neuron. And right, and what I want to show you now is how would we expect you to simulate a Poisson neuron, okay? And again, I know most of you will use the ChatGPT, and in this kind of question, which is probably a reasonable thing to do, although I really highly advise you not to do so. But even if you use it, you need to understand what you're doing, okay? Because the ChatGPT might do 1 or 2 things, and we don't want you to do the third one. So one possibility is that you take a spike, and after each spike, you randomly choose the interval to the next spike from an exponential distribution, where the lambda is RT, and T is the current time of the spike in your recording. The reason that this is not a very recommended way to do it is that you have a lot of problems with the Poisson neuron. The spikes are very probable at the beginning of the recordings and not by the end. So this is not a good way to do it. So the preferable way is to do it based on the idea of the binomial approximation. And what will you do? You will have each small bin, delta ti, and you will choose a randomly number xi, okay? A random number. And you will take it from a uniform distribution. And then you will have this binomial distribution like this, that you will check. Is our firing rate over delta t is bigger than this number? Is it a success or a failure? If it's a success, you will assign 1 at this bin. And if not, you will assign it as 0. So I just really want to explain it again. Please note that the R must be very big in relation to the bin size, and the number of sites is at most 1 at the bin that you choose. Okay? So this is the right way to do a simulation of Poisson neuron. I want to re-explain it in Hebrew. מה שאני מראה פה זה איך לעשות סימולציה של נוירון פואסוני. אז יש שתי אפשרויות. אפשרות אחת זה לעשות את זה בעזרת ההתפלגות האקספוננציאלית. זאת לא האפשרות הטובה. כש-GPT עלול להציע לכם את זה, אז שתדעו שזאת לא האפשרות שאנחנו רוצים. זה יוצר כל מיני עיוותים בתוך הספייק פריים, זה גורם להם להיראות כאילו הם ממש רק בהתחלה של הנוירון וכו'. מה האפשרות העדיפה? אז אתם יוצרים לעצמכם בינים בגודל נגיד של 1 מילי שנייה כל אחד, ואז בכל בין אתם מגרילים האם היה שם ספייק או לא. איך מגרילים את זה? לוקחים מספר מתוך התפלגות רגילה, ועכשיו רואים האם המספר הזה קטן קצב הירי של הנוירון כפול גודל הבין, או לא. אם זה גדול, זה נקרא success, הצלחתי. אז עכשיו אני שמה פה 1. אם לא, אז זה 0. ואז זה יוצר ממש את הסימולציה של נוירון פואסון. So in your second project, you will be asked to simulate such a neuron with a refractory period. 2 kinds of refractory period. This is without any refractory period, and in your project you will use it also when there is a refractory period, and this is something that Izal will talk about during the next lesson, and I will also talk about in the next recitation. Okay, we don't have a lot of time, so I won't go into details regarding how this kind of simulations are being used, but this is very, very commonly used simulation in neuroscience that you want to show how your neurons are working. And this is one of the most easiest one to generate. So for this reason, this is in the course. Yes.
So we said that when delta is almost 0, we go to Poisson distribution instead of binomial. But how small should it be to?
So for example, 1 millisecond is good enough. This is an approximation. And it works really, really great. Okay. So the last thing that I want to talk about are the 2 ideas that Izar taught you today about CV and Fano factor. Okay. So first of all, what is an ISI? By the way, Ori, did I answer you the question regarding the Poisson distribution and exponential and so on?
Yeah, basically.
Okay, great. So the first of all that we want to talk about is the ISI, the interspike interval. Okay, so that we have what interspike interval is the duration between spikes. Okay, this is what I have been written here. This is the interspike interval. So when there is a regular process, it will be constant, right? Because the neuron will fire within every specific time. In a Poisson process, it is stochastic, and it is given by a specific distribution. So for example, in a homogeneous Poisson process, it is approximated by the binomial distribution that is written here. Okay? So here is an example how you can calculate the ISI for 5 bins. Okay, and you have it when the R is 20, so you can read it. There might be, I don't remember if in the quiz we were asked about that or something like this, okay? So this is approximated by the binomial distribution. And if we say that the delta t is very small, then we can see that it starts to look like an exponential distribution. And again, this is one of the proofs that Isao is giving in this lecture. Very good. Okay, and again, Sunday I will talk also about this. Now, yes.
Very small here can also be like 1 second.
Here again, it's approximated by 0, but yeah, 1 millisecond will be fine in the project. Okay. I feel that Araceli, the main thing that you need to look about is the relations between RT and the beam size. So for example, if you have R equals 500, it won't be good. But if you have, for example, 20, which is very big in relation, 20 means about every 50 milliseconds, then 1 millisecond pin is good enough. Okay, so now I want to talk about the CV. So the CV and the Fanon factor are given from the field of Poisson distribution. This is just one of the ways to decide whether you have a Poisson neuron or not, right? Because we said that we want to simulate, but who said that when you simulate a neuron, it looks like a real data? So the idea here is that what we can do, we can take real spike frames and we can change their CV and the Fanon factor. And within 1 minute, I'll show you how we do it in one of these other exams, for example. Okay. So the CV is the coefficient of the variance. We use it only for ISI. Okay, not on the counts of the spikes within a beam, but only for ISI. And in exponential distribution, the standard deviation and the expectation are the same. Therefore, for a Poisson model, the CV should be around 1. And for a regular, it should be around 0. Okay, because the standard deviation is 0 in a regular one. And similarly, the Fanon factor is used only for spike counts. Okay, and in this one, spike counts are for Poisson distribution. And in Poisson distribution, the variance and the expectation are the same. So in this one, the Fanon factor will be 1 if they're the same, and 0 if it is regular. Okay, so let's see a better demonstration of the idea. So if we have a regular neuron, it fires within every specific time interval, right? Therefore, the CV, which is the standard over the expectation, is 0, like here, because there is no standard deviation. The ISI is the same. It's always with the same probability of 1. But if we have a Poisson neuron like this, and here we can see that this one, the ISIs over here look like an exponential distribution, right? You see it? So in this one, the CV will be 0.83, which is much more closer to 1. And please look at the differences in the organization of the spike frames. It looks like they are sparse, but there is some randomness, but there is still organization. And here, when the organization wins, there is no randomness at all, but this is not one of the, this is not how the brain reacts. Okay? So a question, if the Fanoff factor and the CV both equals 1, can we assume that we have a Poisson neuron? What do you say? So as always, not, okay? The answer will always be to such a question, not. Because, for example, let's say that we have a burster. For example, a neuron has no spikes, but when it is stimulated, it bursts. And the number of bursts is Poissonian distributed. Then this is not a Poisson neuron yet. It acts like the CV and the Fanoff factor will be around 1. Okay. So you will read more about it in the paper of project 2. So I won't ruin the party.
Could you repeat that explanation?
I really want to show you these exams. Okay, sorry. So I can repeat it on Sunday. Is this okay? Great. Okay, so we have this following histogram, Einstein histogram of a neuron in the quadris regularis ganglion. I would like one of you to explain what we see here. The numbers are 9 and 10 over here and 0.5 over here. What does that mean about the neuron? Who would like to explain? Yes. Great. Okay. So let's plot the neuron. By the way, the best way to solve these problems are by drawing. So how would such a neuron look like, Julio?
In terms of the supply to the brain,
So the spike frames
Yeah.
can look
spike and then either
right.
spike again.
So one possibility is that it will be interleaved, that you have 9, 10, 9, 10. Right? Another possibility is that you will have all the 9s at the beginning, and then by the end, all the 10s. Okay? But each one of them is possible in relation to the description of the ISIs. Is that clear? Yes, it can be interleaved or whatsoever. Or it can be 9, 9, 9, 9, 10, 10, 10, 9, 9, 10, 10, 9, 10, 9, 10. If there is someone here who does ballet, it's one of the nice, right? 8 like this, and then 8 like this, and then 4, 2, 1. So it's about the same idea. Great. Okay, but let's take anyhow. The reason that I showed you this, you will see it in a moment, because these are kind of 2 limits of all the possible organization, right? Because it can be either one after the other, which is transitioning really fast in between them, or they can be like separated kind of populations, right? Did you understand what I said? Mm-hmm. So these are the most far limits of the organization of the data. So first of all, we need to calculate the CV. The CV is of interspikes or spike counts. Which one? Interspike, right. So we can use already the histogram, right? Do you understand why? Okay, so what is the standard deviation of the interspike? Let's see. So we need to calculate the variance. So the expected is 9.5. Do you understand why? Half of them are 10, half of them are 9. Therefore, the expected is 9.5. And the variation, given the formula variation, is the probability for the first 9 minus the expectation squared, plus the probability for the second one minus the expectation. And if you calculate it, this is 0.5 squared, and the standard deviation is the root of this 0.5 squared. Therefore, 0.5 over 9.5, which is around 0. Okay? Did you understand this calculation? Good. Now, what we want to do, no, this is not what I wanted to do. Okay. Now, what I wanted to do is the following. Now I want to calculate the Fano factor, right? So I want to ask myself, what is the possible of spike counts within each 100 milliseconds, for example? Okay, so I take a beam of 100 milliseconds. So if I take this beam here, then I have 10 spikes. Do you understand why? The interval is 10, so I have 10 spikes. And if I take the interval here, I have 9 spikes. I have, sorry, 11 spikes. Okay? So I have a probability, for example, for either 100 or 10 spikes. Okay? And then I can say the variance between them is let's spin. The variance here, it's about the same, right? So you have 9, 10, 9, 10, and you have it for 100 milliseconds. It will act the same across each beam, right? So the variance here will be 0. But here, this is my way to show you the biggest variance, right? So the variance here is 1. Okay? So I know that the variance is between, right? It's 1. No, I need to calculate it. Okay. So let's say the expected is right in between them, which is 10.5, right? So now I want to calculate the variance of each one. It's 10 and 11. And then I can use here the same formula for variance. And then I will have variance is 0.5 squared. Did you understand what I say? And then when you divide it by, this is like the maximal possible variance. And even in the maximal possible variance, you're still lower than 1. You're around 0, even at the maximum. Therefore, even when you use the Fano factor, this is not a Poisson. Okay? So you look really, really tired. So I would just highly recommend to see also this pacemaker neuron over here with the normal distribution. Okay, this is just about the same because you have the STD is given and so on. So this is even a bit easier. The only kind of confusing thing is the fact that they use it for normalized distribution. So please look at it. It is the easier exercise and see that you fully understand it. And in your quiz, as far as I remember, you have a question about a neuron like this. But instead of the two spikes that are together, they are much more far away, for example, 510 or something like that. And then this kind of question becomes more Poissonian-like, and I want you to see it. Okay, so when you do the quiz, try to recap what we did here and to solve it again with the different numbers, and then you will see the differences. It's really cute. You know, cute depends on who you are asking. Okay, was it okay? Be strong and see you on Sunday. And tell Sophie if you feel that you need more than Sunday, maybe for the following Wednesday, or I don't know. We will do something bigger. that I will send, sorry,
some videos and
regarding this subject?
yeah. I don't know.
Ah, yeah, okay. Yes, please remind me that I need to prepare it.
But that's okay, I mean, the week is done now and you can just.
No, I need to do it. I'll do it during the weekend, no problem. Yeah, this is, I know, this is a very hard part of the course. I think the hardest. Yes, Austin.
Over ergodicity break.
The ergodicity breaking, I can talk with you now. I have 15 minutes that we can talk about the project.
And you also said speak about question 4 and 5.
Yeah, so I will say it really fast. So the SNR, you needed just to use the expectation of both the signal and the noise, right? And for those of you who use the variance, it became the wrong answer. Okay, so I just wanted to say that in some cases, people do use the variance and not the expectation. So you were not confused, it's okay. I will see it as a point. It doesn't really matter because all of you passed. You should just know that you are not mistaken. You can, it just depends on the definition. And I meant that you will use the explanation. Yeah.
Just because that was the first time I'd seen, the first number is mean and the second number is variance?
Yes.
Okay, that was not
Yes.
anything else.
Yes. The first number is mean.
Is it variance or standard deviation?
And not a very standard deviation, yes.
Okay.
And yeah, it's a very common way that we do it also in the course. And you can see it also here. This is the expectation and this is the standard deviation. And about the convolution, the mistakes were just not using the normalized window. Okay, so just know that you need to normalize the window before you use it, and double check that when you use. Sorry, for whoever is not staying, please just it will be a bit hard for me to repeat it again. Also, in your project, when you use convolution, please note that the title is normalizing the window before using it. Maybe you should do it if you want to be on the, I don't know, if you don't want to make any mistakes. Okay, so please know that you need to normalize it. Otherwise, it just makes your data really high or low, and it depends on the size of the window. So you need to normalize the window before you are convolving.
Yeah, sorry, just about the notation of the Gaussian, like it's.
Here,
And
here.
then it's mean.
And normalize distribution, expectation, and standard deviation.
Because on Wikipedia it's really written like N, mu,
Mu
and
and
sigma squared.
so this is the variance. Now I know that this is the standard deviation, but I recheck it with this okay. But right here, so there is no chance that I remember anything if it's not written. Okay. Yeah. Now about the project. Great. Questions?
About ergodicity.
Yes.
So the example variance, since it is in a fixed time, I was just wondering if we could use like a window, because how can we evaluate the variance in a fixed time?
Yes. So you should use a window. Yes. Across a specific window. And then I told Araceli also in the break. So what I would do is use it across all the possible subsections of the subject. Okay. And not only yeah. You know, for example, for the full subject, it will be the best, and for one, it will be the worst. But then you can look at the distribution and say, okay, this is irrelevant. I'll take it from 4 and so on, 4 or 5 or whatsoever. Okay, because this is just about the second question about SNR. The more samples you have, the better SNR you have. So you can say that you see that the SNR is much better from 4 and so on. And then you don't need to use one subject as a subsample.
So basically, we choose the window and we also choose the number of subjects.
Yes.
Okay.
But you choose and then you run all the possibilities. Do you fully understand me, Elsteady? That you need to do it across all possible subsamples, across all possible sub number of subjects. 10, 20, 50, and so on. I have time, wait. Okay, but then you can say, for example, from 4 subjects and downward, it is irrelevant because the SNR is not good enough. Okay. Yes.
So does that mean we also need to calculate the error rate or the ergodicity rate across all time samples?
No, it's
Or
okay that you will choose, for example, the 100 milliseconds or something.
And just an arbitrary 100?
Yes, yes,
First, last,
yes.
just once?
I would take both, first and last.
Okay.
Yes,
The definition of the ergodicity rating.
sorry. The reason for doing both, sorry,
Yeah.
for both first and last is that you need to see that the process is also stochastic. Not stochastic, stationary. And if it is stationary only if it's the same in the beginning and in the end, or all along the process.
Right.
Okay? Sorry.
Also, like the ergodicity rating in that paper is defined as a function of time.
Yes.
So does it mean that you have to calculate the total variance until some time point, and taking the time points until that time t, and then calculate.
So some people say that after, for example, 1 second, you can look at neural data as if it is a new data, if it is a new trial. So for this reason, in the paper, they do it across time. But the right thing to do, if you want to be more accurate, is to do it along the number of subjects.
Okay.
Okay, so what we wanted to do is to do it along the number of subjects, which is how we define ergodicity.
And,
Do you understand? The x-axis should be different in your
Yeah.
subjects, yes.
and the subjects, I guess there is no like right order of subjects, so do you have to take them?
I would average across all possible subcircles. For example, if it's 4, I would average across all possible 4s of the population. And if you really want to do it and make me really satisfied, so also add the standard deviation. It's distribution.
Yeah.
Because again, we are talking a bit more scientifically. You never show something without standard deviation or normalized standard deviation. Do you know what is the normalized standard deviation? So you have this is called SEM, and this is SED that you divide by the square of the number of samples minus 1. Okay, and commonly it's more elegant to use this one. I would use it for every plot that you draw in this course, yes, because this is more scientifically accurate. Okay. Any more questions? Yes.
Next exercise, it was 2, where you have to simulate the wave, the sleep waves. And the second part, it says you have to do for at least 4 seconds. But in the second part,
Yes, he said that you have the SNR calculation, yes.
in the second part, the one with nonce.
Yes.
It's very fast. So, is it okay to take less for the, because if you plot 4 seconds, you basically see a blue thing, and you don't see.
Do the 4 seconds and the zoom in. Okay. Now, I really recommend about, again, when you simulate the noise, simulate it many times, so you will have something more clear regarding the graph. Do you understand me? Don't simulate only once the 3 trials and 4 trials. Simulate it again and again until and average across the simulations, and then you will have something which is more smooth. Okay? And Sophie, again, please write all the clarifications. I'm sorry for asking you to write so many things. You can also, Araceli, I think that you can also help us.
Sure, yes.
And I don't care who will write it. I can also add you as a manager in the WhatsApp group. But just please write all these clarifications because I think, yeah.
That I understand half of them, so I cannot.
Okay, no problem. Julia, you can also concentrate. Yes.
And about exercise 2, when I'm asked to, just conceptually, when we're asked to plot the noise over trials,
Yes.
in my head, what that means is I'm expecting like a blank plot, right? Like I'm expecting it to average out to 0.
Yes. Not average to 0. I mean, like the basic rule is that the more samples you have, the SNR is better.
Yeah, but if we're only plotting the noise, right? Because it only asks like plot the noise component of the average
Yes.
signal,
Yes.
then I should expect to see a plot that's 0.
All along the way.
Or like somewhat, right? Like I can see it decreasing to the point where it's like
Yeah,
slowly, it's like minus.
Very fast decreasing to the 0. Yes.
Yeah, but I'm seeing, but okay.
Yeah, you should start with very high values because the amplitude is 10 times stronger than the noise is 10 times stronger than the signal. So it should begin like really, really high noise and then it should decrease. Yeah.
I read that exercise was slot SNR versus the number of simulations. Because SNR is like the actual noise.
No, I meant that you need to, if you want this curve to be more clear, I would simulate it again and again.
No, but in Iran's fraction, where you have to plot the noise versus number of simulations.
Yeah, we wanted that you will see the reduction in the noise and not yeah. I mean, reduction in noise is a bigger SNR, right? Yeah, the signal is bigger. Yes. So yeah, you're right. So the signal will increase, but we didn't want it. Didn't ask you to plot the SNR because this is less visual. We wanted to see that the noise is decreasing very, very fast. And then you need to decide what is the number of samples that you need in order to have a very good SNR. Great. Okay. Thanks for coming.
Thank you so much for your.
You're welcome. רגע, מה קרה פה?